Good morning, everybody. How are we doing? I heard there's a math test today. No? Oh, you had one on Monday? Other people have it today. Yeah, tests always happen, even after you leave school. All right, we're finishing up. I can't remember what chapter we're on and moving on to whatever that number is plus 1. Are we on 26? Yeah, 26 and then moving into 27. This is an example problem, but before we get there, let's do something like totally practical. It's probably like the one time in Physics 4B you're going to get any practical information. I copied out very long time ago part of my PG&E bill, okay? And the reason I want to talk about this today is because of that right there. What the heck is a kilowatt hour? It's not a kilowatt per hour. It's a kilowatt hour. So that is literally a kilowatt times an hour. What's a kilowatt? It's 1,000 watts, right? And then in an hour, there's 3,600 seconds. So what is that? 3.6 times 10 to the 6? Watts times a second. What's a watt? It's power, but what are the units? What is it? It's a joule per second times a second. So what's a kilowatt hour? It's an energy, right? A kilowatt hour, when you get it all out, is just a conversion factor of energy. So what does PG&E charge you for? Energy usage. Not power usage, but energy usage. And on this bill, right, they're charging a certain amount per kilowatt hour, right? So it looks like they're charging about 12 cents per kilowatt hour to just make the electricity. So why is my bill so different than just 12 cents, right? Well, what's distribution? It's almost 10 cents per kilowatt, or 1 cent per kilowatt hour. Yeah, so they're charging me to make it, and then they're charging me to get it to me, distribution. But I thought distribution was transmission. Wait a second, transmission shows up down here. Wait, so what's distribution? If transmission is getting it to me, then what is distribution? Sharing it with my neighbors. It's one thing to get electricity to a town. It's another thing to make sure that the entire town is hooked up, right? So make it, share it, send it. We'll get to that in a second. Transmission rate adjustments. We weren't charging you enough, so we'll charge you more. Reliability services. Public purpose programs. I had to call this one up. I had to call them and say, what the heck is this on my bill? Public purpose programs. Were any of you visited in elementary school by the PG&E hat mascot? Did you know PG&E had a mascot? It was a big hard hat, big fluffy hard hat, person in a suit. No? Well, apparently part of my 1.24 cents went to supporting that. And other programs, like there's low income, like change all your light bulbs out for LED bulbs. There's good stuff in there, but I questioned the mascot one. Nuclear decommissioning? Sure, help clean up stuff. Competition transition, no idea. Energy cost recovery amount, that's a negative, so they gave me money back. DWR bought, what's DWR? Don't know. New system generation charge, whatever that means, right? So there's a whole bunch of, and a lot of these are not things PG&E makes up. They are things that are mandated by state law, and some of them federal law, about how power is sent around. So in the end, right, you're charged a certain amount for the energy that you use. So how do you first calculate, right, how much this costs? And then what do you do about it? Okay, so let's just do an example, right? This is an old-fashioned incandescent light bulb. So the old-timey, like your parents' and grandparents' light bulbs, right? We have all these fancy-dancy LED light bulbs and compact fluorescents nowadays, right? So let's figure it out for one of these old-timey light bulbs, okay? Are there lights in your house that are on for 8 hours a day? Okay, well, no, like light bulbs. You like your kitchen light bulb isn't on constantly? No? Living room? Bedroom? Like from the hours of 6 p.m. till, I know, 1 o'clock in the morning when you're still working on your homework? Right? And then again in the morning, right? Like, is it easy to like push a light bulb to 8 hours a day? It's possible if you're not careful, right? All right, so they're doing a 14 cents per kilowatt. Does anybody know what the going rate is right now? For per kilowatt hour? Yeah. The answer is nobody knows because it changes every 5 minutes. There's a auction that takes place. Auction, in quotes, because the computer's all in charge of it, that regulates the energy markets, and every 5 minutes the value changes. On average, for tier 1 energy use, which is the, we got to talk about that, don't we? Do you see how it says baseline usage right up there at the top? Were you aware that PG&E and the state of California get together and decide how much energy you're allowed to use? It's called the baseline usage, okay? And by state law, there's a cap on how much PG&E can charge for that baseline. So it doesn't say what my baseline usage was on this thing, but it usually hovers, it changes from, depending on what time of year it is. But let's say it's like 300 kilowatt hours. So that means I'm allowed to use 300 kilowatt hours of electricity every month. Now, if I go beyond 300 kilowatt hours, do they just shut off my power? No, they raise the rate. And so you get into these things called tiers. And there's 3 tiers nowadays. I believe the first tier in California caps out at 22.5 cents per kilowatt hour, 23 cents per kilowatt hour. Tier 2 caps out at 50-something cents per kilowatt hour. And tier 3 is unlimited and usually starts at $2 per kilowatt hour. Okay? So if you want to lower your electricity bill, what do you want to try to do? Not go past your baseline, which usually means use less, right? But it could also mean use more if you have, say, like solar panels. Because solar panels give power back while you're trying to spend it, so you can try to stay in the lower tiers. So just be aware of that. You can see here on this old bill that they're going from 23 to 20 to almost 30 to 50 cents. It's much bigger jumps now, especially with the new energy markets. There's a website that the states or PG&E's require, somebody's required to run, that will show you almost in real time what the electricity rates are. Yeah, I think they all have to include this exchange. Anyway, it has to do with money, and I have no idea what's going on when it comes to money. So it's quantum mechanics I get. Accounting? Black magic. Just black magic. Okay, so let's get back to this. So 100 watt light bulb, 8 hours a day for 1 month. So we want to find cost, right? So if we're going to find cost, we know that 1 kilowatt times an hour is 14 cents, right? So we need to find out the total amount of kilowatt hours that this light bulb has used up in 1 month. And then once I know that number, I multiply by 14 cents and I'm done, right? So how do I find the total kilowatt hours that this light bulb consumed? What's the wattage of the bulb? 100. What's that in kilowatts? 0.1 kilowatts, right? 100 watts divided by 1,000 gets me 0.1 kilowatts, right? And then I run that 0.1 kilowatts for 8 hours in one day, right? And we're back to basically chapter 1 conversion factor stuff now. And then how many days are there in 1 month on average? We'll just go with 30. 30 days in 1 month, right? So what am I left with here? Okay. I have, unit-wise, a kilowatt hour per month, don't I? So this will be the number of kilowatts in 1 month. So I take 0.1 times 8 times 30. Did I do this? Yes. I got 24 kilowatt times hours per month, right? And so if I want to know the total cost, I take that 24, I multiply it by 0.14 of a dollar, which is 14 cents, right? And I get a total cost of $3.36 for the month. Which doesn't sound bad, right? A little over $3 1/3 to run a light bulb every day for 8 hours? Great. How many light bulbs are there in your house? Do you have light bulbs on the outside of your house that run all night long? Do you install Christmas lights? How much does a Christmas tree cost? Like, it can add up really fast, right? Okay. So how do you make it more efficient? How do you beat the system? Turn off the lights, right? Why, as a father, am I constantly running around telling people to turn off the lights? Because I'm tired of paying for PG&E, right?
Aren't they like equivalents now?
Okay, yeah. So this is the old-fashioned light bulb, right? A LED, so an equivalent to a 100-watt light bulb, uses it's anywhere from 7 to 10 watts of power. So like basically divide by 10, right? Okay. So if you can get the same amount of light for 1/10 the power, what does that mean for your savings? You basically say you divide by 10, right? And so instead of $3.36, this would be 33 cents, right? So that's a big savings, right? So you're like, hooray, LED light bulbs everywhere, run light all the time, which is essentially kind of what people do now, right? We are more efficient in the state of California, believe it or not. We're still under like what it was in the 1990s and early 2000s. Now that we've transitioned a lot of our light bulbs over to LEDs.
Do machines, do they still use power when they're just plugged in but not being used?
I paid him to ask that question. New York Times. How much power do electronics use when they are turned off? Berkeley. Yep, Berkeley. Lawrence Berkeley National Labs keeps a database, they did for a while, I'm not sure they do it anymore, of things, computers, notebooks, desktops, printers, game consoles, okay, all kinds of things, receivers, surge protectors. The amount of electricity they use while being used, while being asleep, and when being off. So you're probably familiar with the idea that like, okay, let's just, by show of hands, how many of you have like an Xbox, PlayStation, or like a cable TV box that gets you to, okay, that's pretty much everybody, right? Okay. So when you push sleep on that game console or set-top box, right? What have you just told it to do? Sleep, right? Your cable top box probably has like maybe a DVR in it or something that like is recording stuff for you. But even if it doesn't, most of them when you go to sleep, so set-top box, digital cable, no DVR. So no like drive inside storing anything. On with the TV off, average is 25 watts. On with the TV on is 30 watts. Off by pushing the remote turn off button, 20 watts. You've turned it off. You've really just put it to sleep, okay? But it's still taking almost the same amount as if it would when the TV was on, right? Why? It's going to do things. Okay. With a DVR, it's even worse. Not recording TV off 30, not recording TV on 30, off 30. Satellite. Get it through Dish Network, or nobody does that anymore, right? It's the same. No matter whether it's on or off, it's all 17. Your television. Get the right kind of television because they had different kinds here. Computer monitor. Computers. Your notebook. Fully on and charged. If it's not a gaming laptop, it's like a standard laptop, is 30 watts. Fully on and charging, this varies quite a bit, but the average is 50 watts. Off, like you've turned the computer off, you've clicked shut down, right? To put the, is drawing 10 watts. That's plugged in, the computer's off. It's not charging 10 watts. The power brick, just plugged in, not connected to the computer, 5 to 10 watts. Just sitting there. Okay? And when you put it to sleep, about 20 watts.
How many watts are the adapter?
So this adapter for mine here is a 130 watt adapter. It doesn't always use 130, it's just it can get to 130, right? Okay. Gaming laptops have adapters that run 200 watts, right? Desktop computers are in the range of anywhere from 200 to 500 watts, unless it's a gaming rig, in which case it can go up to 1200 watts. When my computer is running everything full tilt and I'm doing my flight simulator and I'm pushing pixels and the computer's hair is on fire and everything's going on, okay, it clocks in at 800 watts. I have 800 watts is like space heater territory. The place where I have my gaming rig, that room heats up in the wintertime. Well, and in the summertime, but in the wintertime, like I don't have to run a space heater in there. All I have to do is play games. Right? So, yeah. And when computers are asleep and when televisions are asleep, they aren't really asleep. Like they're still drawing electrical power. These are called energy vampires. Why are they called energy vampires? Because they suck your blood. Right? No, they're not doing anything. Like literally, is your TV doing anything if it's not displaying a picture? No. Why is it drawing power, right? So how do you beat it? How do you fix that? You can unplug everything every night. Nobody's going to do that, right? But like the things that I don't need all the time, like the Nintendo Switch, I haven't touched in years, right? Game consoles, TVs, that sort of stuff, I have them on a power strip. And the Switch is easily accessible. And now it cannot get power, right? To sleep or do anything. Now, do I put my cable modem or my Wi-Fi system on a power switch? No, I want that one on 24/7, right? There's some things that should be left on. The internet's one of them, because I got lots of devices in my house that have to talk all night long and do backups and things like that, right? But there are other things that don't. Televisions, most computers, that kind of thing, right? So you want to... Here's an experiment for you to try to save the planet and your bill. Before you go to sleep tonight, whatever room you're in, maybe try the whole house, that's even more fun, but if even it's just your room, turn off the lights and then count how many things are blinking back at you. Not the wild animals and their eye shine, that's different. But just the little LEDs of things. Like walk through the living room You'll see a little glow maybe from the TV's little light telling you, I'm ready, I'm ready, I'm ready. You might see the lights on the wireless router or something, right? Okay, but there's a lot of LEDs shining bright. Why does my stove have to tell me the time? It's one I haven't been able to figure out how to turn off, right? Like, why? I don't care if my stove knows what time it is. I want it to make food on my time. Anyway, so it's just weird. It's just weird. So, go kill the energy vampires. That's the goal. That's the site, by the way, that listed. And it's just standby power. You can go look up standby power on the web, and there'll be various sites that will give you all of the information about what things do. It's been getting a little bit better. I think like Comcast and Time Warner and Cox Cable, all of them were caught out, and Congress had to intervene and tell them you have to make your stuff more efficient. Like there's no reason for those things, especially the ones that don't have DVRs in them anymore. There's no reason for them to be using power when the user is not viewing television. They were just being lazy. They didn't want to redesign their stuff. All right, so here we are. 27. This is kind of the big chapter, as it were. Why can't I find my mouse? Never can find my mouse. Of like this unit. I saved 3 days to do it, and we've kind of got a lot of ground to cover in this one. And this is where everything comes together. We're going to be doing circuits. We're going to be doing parallel and series. We're going to be doing capacitors and resistors together. Like it all comes together. And those of you who are electrical engineering majors that have been waiting the whole time for the circuits part of class, this is your moment. Okay? I'm about to show you what you're going to do for the rest of your life. Counselors are standing by. But we got to talk about batteries. Because I've alluded to this a lot. Batteries don't do what most people think that they do. Because batteries don't provide charge, they provide push. Where does an electrical circuit get the charges that it needs to operate? A circuit consists of a battery, capacitors, wires, resistors. Where does the charge come from that's going to be doing work and energy and stuff like that in a circuit? No, it doesn't come from the battery. It comes from the wires and the capacitors and the resistors itself. The charges are in the conductors, right, that make up the circuits. And so batteries don't make charges. They push them around. Batteries, so in the analogy of like water pressure in a plumbing system, right? We often feel like the pipes need to fill first, and that's true initially. But the pipes in your house are filled with water all the time. You turn on the faucet, water comes out, right? The water's already there. The charge is already there. The pressure system coming from the city, or a well if you live in the country, that is the battery. Batteries provide pressure. They provide push. They get charges moving through a circuit. They don't provide the charge in the circuit. And so when you have a battery, okay, and it's hooked up to a load, like a resistor or something, okay, we need to talk about why some batteries go flat or go dead or lose the ability to push. I mean, obviously they're running out of some kind of energy, but a battery's job is to give a potential difference, right? It's to allow for that push to take place. What I've done here is I've drawn a schematic of a battery. And inside the gray would be what everybody thinks of as the physical battery itself, right? The AA, the AAA, the 9-volt battery in your phone, whatever, okay? And then there's some sort of load on that battery, in this case a resistance, but the resistance could be your phone, could be your washing machine, anything that's using electrical energy, okay? So And then I've got a little tiny resistor that's sitting there sort of inside the physical battery. When a battery goes flat, or I don't like this word, discharges. Like, isn't it like just baked into the language we use around batteries, right? You charge a battery, you discharge a battery. None of that's happening, right? Okay. When a battery stops being able to push, its internal chemistry has gotten to a state where all of the energy to push is being consumed by itself. Every battery has something called an internal resistance. And when a battery is fully, can I use the word charged even though you guys know it's wrong? It's sort of just standard, right? Okay. So when a battery is fully charged, it means that its internal resistance is as low as possible. And so therefore, if you hook it up to a load, if that little r is practically zero, then all of the voltage of that battery can go to that load right there. But as time goes by and the chemistry of the battery changes and alters, right? The push has to come from somewhere, and it comes from the rearrangement of chemical bonds in the battery. The internal resistance of that battery is increasing and increasing and increasing. More and more of the push is being consumed by the battery itself. Until you get to a point where the potential that the battery can provide and the internal resistance equal each other out. Now, I know voltage isn't resistance. We'll fix that in a second. But the idea here is that your battery in your phone, right, when that reading changes from 100 to 90, 80, all the way down to 10, 20, turns red. Battery mode, you're all going to die, right? Okay. What the battery is trying to report is, no, I can still provide voltage. It's just that I'm having to push against my own chemistry too hard. And so a 0% battery means there's nothing left for the outside world. The potential's still in there. It's just it can't get out. Okay? So what's going on here? The voltage difference across the battery, okay, otherwise known as the terminal voltage, is equal to the difference between its EMF, that's that funny E right there. So EMF is this symbol. It's like a uppercase cursive curly E. I think in most like printed textbooks they'll do like a it's like a curly E that has like a Elvis hairdo on it or something. I don't know. Okay, right? It's kind of a curly script italicized E. That's called the EMF. Quite possibly one of the worst named things in all of physics, because EMF stands for electromotive force. What are the units of EMF? What are the units of voltage? Volts. What's the unit of Ohm's law? A current times a resistance. Volts. So what does EMF have to be? Volts. You can't subtract apples from oranges, so they both have to be volts, right? So EMF has units of volts. It's a voltage. Okay? This over here is Ohm's law. This also has units of volts. Okay? So what does it do? So this is called the terminal voltage. Not because it's killing you. Okay? But this is the voltage you would measure across the positive and negative terminals of the battery. That terminal voltage will be equal to the EMF of the battery if and only if what is true? The internal resistance is 0, right? So if little r is equal to 0, then the terminal voltage is equal to the battery's actual ability to push, and that's going to be the case for all of the batteries we put in any of our circuits. Okay? The reason we're telling you about this and teaching you about this is we're trying to clear up misconceptions around how batteries kind of work on the inside, right? We will always assume EMF and terminal voltage are the same because we're going to use ideal batteries that have no internal resistance. That current, by the way, that's there, that's the movement of charge through the battery, through the circuit, right? That current would be the same through the internal resistance as it is through the external resistance, because this is all in series. More on that in a bit. But if little r, the internal resistance, is any bigger than 0, there's going to be a discrepancy between what you measure across the terminals and what the battery is trying to provide. Since we're here, let's just talk a little bit about how you maintain the health of any battery, make them last longer, especially batteries that are in your devices, be they your iPads or your phones, that electric cars, very similar idea. Does anybody know what you should do to keep batteries healthy for long periods of time? Because there's a lot of bad. Keep it to 20 to 80%. That is the best rule of thumb for any battery pretty much in any device nowadays. In the old days, it was a little bit wrong with the nickel-cadmium batteries, but today's batteries in all of our devices, the lithium-ion batteries that power just about everything, they really don't like being over 80% for very long. You can charge them to 100%, no problem, as long as you're going to use that within a reasonable period. But if you're the kind of person that uses your phone and notice it, you charge it to 100, and then you notice by the end of the day you're only down to 70, you really shouldn't be charging to 100. You should be charging up to 80 and just stopping there, and as long as your normal daily usage takes you down to 20%, you're fine, right? If you're a heavy user and you need all of that power, by all means, charge it up. As long as you're... Batteries like to be cycled. What they don't like is being pushed to their full amount and then only being used a little bit. Okay? That's actually very bad for their internal health, the resistance that builds up and their ability to keep functioning. So if you have trouble with your battery like after 2 years in your phone, and by trouble I mean like it doesn't hold a charge for more than an hour or something like that, you might want to take a look at your sort of usage patterns. Apple and Android operating systems both have features that sort of show you what your battery's doing and like how much it charges. Both of them support options for like don't ever charge past 80, or use intelligent charging where it like tracks how you use your phone during the day. And it like knows if you plug it in at night, it can charge up to a certain amount, and then maybe right before you wake up, it will charge that last 100%. There's all kinds of intelligent ways software engineers are doing to try to help you keep your batteries lasting longer. But you can definitely do that. So the 20 to 80% rule is really useful, especially with electric cars. Oh my gosh, do not put batteries in the refrigerator. Have you heard that? Store your AA's and AAA's and all that stuff in the freezer. If there's something that all batteries hate, it's cold. Batteries just don't like cold. It takes more energy for the battery to operate in the cold. And then you take it, you freeze it, you plug it in, and now it's just like, I'm just use a ton of energy right now, right? Don't waste the freezer energy. You'll hurt the battery. Just don't put them in the freezer. You don't need to. So yeah, those are try to avoid extremes of operating temperature if you can. I mean, we do live in Fresno, so extreme doesn't mean 100 or 120. Like, just don't operate your phone in the sauna or something like that. But too cold can also really sap your phone's energy. Okay, if you're down at freezing temperatures and you've got your phone out and you're using it, it's going to get used up faster than it would otherwise. Beyond that, you really have to work hard to try to get a battery to explode unless you're the Samsung company. They seem to have a pretty good track record. Do you guys remember that, where phones were exploding on airplanes? And for a while there, if you had a Samsung, what was that, the Note 7? If you had one of those, you weren't allowed on an airplane because they were exploding.
They also have logging machines that were doing the same thing.
Probably, yeah. The batteries in those, Samsung had decided that For some reason at the time, all manufacturers, Apple, everybody, were trying to make phones as thin as possible. It was like a race to thinness, right? So Samsung decided, oh, we can take out that 1/10 of 1 millimeter gap we have around our battery, right, inside the phone case and make it more thin, more thin. Well, what happened was that gap had to be there because batteries change their volume depending on how hard they're working. If they're not working, they shrink, and as they work, they kind of expand. Some gases in the lithium ion, some gases form inside of the battery, and as it stops working, those gases will return back down. But what happened is the engineers that designed the mechanics of the case shrunk it. The engineers that were working on the batteries kept them the same size, and now the batteries were fitting, but just barely. And when the batteries went to swell a little bit under usage, they ran into pokey parts inside of the case, and then the batteries got poked. They let all of the hydrogen-based gases out. And what happens when you mix hydrogen with oxygen and some heat? Fire. Okay? So, yeah. Batteries need space. I don't want thin batteries. I don't really want thin phones either. Lightweight I'm not opposed to, but I'm not sure. But I also grew up in the era of phones being bricks. The original mobile phone was like this. You wore a backpack. Pretty cool. All right. What's that? Oh, yeah, like when you're AA's, AAA's, they get that crusty stuff inside of the battery case, like they've leaked or something. So those are alkali batteries, and alkali batteries are notorious for sort of swelling and causing problems. A lot of people will try to use baking soda to clean that up. Use vinegar. It's an alkali. It's a basic crystal salt that's on the terminals. Get some white vinegar on a Q-tip. You can just clean that stuff up right away and then dry it off and you're golden. But yeah, it's because the alkali batteries will swell and leak their alkali solutions out. Don't recharge an alkali battery. You heard it here first. Only recharge rechargeable batteries. All right, where were we? We were right here. Yeah, play. Okay.
These two sets of batteries appear identical and show approximately the same reading on a voltmeter. But there is a difference. When a light bulb is connected to this set of batteries, the bulb lights and the voltage of the batteries remains about the same. When we do the same with this set, the bulb fails to light and the voltage of the batteries drops to nearly nothing. This set of batteries has been heavily used and has a high internal resistance.
So did you notice how the voltage reading was high when the batteries weren't under load? That's the terminal voltage and the EMF being the same. It only went to zero when the circuit was closed, right? When an external load was applied, and then the battery's like, well, I can't push to that, right? And so that's why the voltage drops. When you're testing batteries, you need to test them under load. You can't just test their terminals. Otherwise, they'll always lie to you is basically what they'll do. Lying bastards. All right. So let's move on to series and parallel resistors. We've done this before. We know what series and parallel are, or do we? If I show you a circuit diagram, can you identify which ones are in series and which ones are in parallel? Maybe. Maybe. Some of us are like, I don't remember this. How do you know when things are in series? There's no junctions between them, right? So if I take a resistor and then another resistor and they're just connected directly to each other, all three of those resistors, 1, 2, 3, are all in series through this battery, right? Because there's no junctions between them. But a parallel situation, I'll do that long side, that short side. There we go. These three are all in parallel. And how do we know they're in parallel? Junctions. There's a spot where wires split. A wire turns into two, okay? Or two wires turn into one. Those junctions are dead giveaways. One of the things you're going to want to do, see if I can demonstrate this. My computer isn't being very friendly today. Let's do it this way. You can do this with both of the chapters, the chapter that involves capacitors and the chapter that involves resistors. You go to the modules, and let's see, we first encountered capacitors chapter 25, right? Chapter 25, click any one of the book links, doesn't matter. Because what we need is the table of contents. Come down here to chapter 25. Come to questions and problems. Okay. All you need are the pictures. That's all you need. Don't worry about what the problem's asking. None of that kind of stuff, right? But if we just look at these diagrams right here. It didn't do it. Here we go. Okay. Let's just look at these pictures, okay? The A picture right there. Can you name any of the capacitors that are in parallel? C1 and C2. And then you combine C1 and C2 and it will be in series. Notice you can go through this entire chapter, end of chapter, right? And there's going to be some pictures. Oh, what are those? Those are parallel, right? Which ones are in series in that picture? Okay, so you can go through and like quiz each other. Just look at the pictures. Don't worry about what the problem said. Ah! What are those two right there? Those are in series, right? It's a homework problem, right? But you can go through here. There's a lot more pictures. Oh my gosh. Maybe we shouldn't do this. Maybe this gets too scary. But just look at the pictures. Don't worry about the problems asking. And practice identifying whether they're in series or in parallel. And how are you going to know if you're right? You're going to need somebody else. And I tried ChatGPT on this, and it didn't do a good job. It has a real hard time. You want to have some fun? Ask it to draw you a schematic diagram with 3 resistors in parallel in it. Talk about hallucination. Like, the image generator goes wild. It is bizarre. You can do the same thing down here in chapter 27. Okay? If you go to questions, right? Oh my God. Ooh! R1 and R2, series or parallel? Parallel, and then their combination will be in series, right? And you just, I gave you this one. Good luck. There's an easy way and a hard way. I didn't give you that one, but it's a good challenge too. Anyway, if you can just practice seeing things, which ones are in series, which are in parallel, that is going to help you so much. You just need to be exposed to different visualizations of this in schematic diagrams. I found a website, I think it was Khan Academy, that had like a little quiz that show you the pictures and you answered, is it series and parallel, right? So there's resources online for practicing this kind of stuff, right? And you just need practice, not so much with solving the problem, you need practice of that too, but that basic skill of being able to identify series and parallel connections. All right, back to this. Give me my mouse back. So, let's talk series and parallel and what's the same and what's different. So when it comes to resistors, we're going to be using Ohm's law over and over and over again because this is the key connection between the voltage in various elements of the circuit, the current, and the resistance that we've got. Like we did with capacitors, where we were worried about charge and voltage and capacitance, Now we're worried about resistance current and voltage. So we want to try to identify things that are the same and things that are different in these different arrangements, right? And so we're talking about current and we're talking about voltage. So for the series case, current that comes out of the battery, what do you think? Is it going to be the same in all three of those resistors or different? Remember, think of current as flow. Same? Current is charges coming out of the battery, right, being pushed around. And any charge that passes through R1 has to pass through R2. And it has to pass through R3 before it can get back to the battery. So it's the same amount of charge per time that's flowing through all of those things, which means that all of those currents are identical, right? In other words, current is the same or equal. But what about potential? What about the energy that something uses? How do we know how much voltage R1 takes? If we know the currents are all the same, then how do we find the voltage? Ohm's law. There's a box up there, right? Okay. So the voltage will be the current times the resistance. If the resistance is different, will the voltage be different? Yes, right? So this leads us to the conclusion that the voltages are shared. Whatever the voltage the battery puts out gets split up or shared across all the different elements of the circuit. So if the battery is putting out 10 volts, and the first battery uses 6, and the second battery uses 1, how many volts are left over for the third resistor? I think I said battery, I meant resistor. 3, right? Because 6 plus 1 is 7, and then to get back to 10, I need 3, right? So it would be 6, 1, 3. It's like conservation of energy, right? You can't use up more potential energy than you start with moving around the circuit. So voltage is split up, or we use the term shared in the circuit. Okay, so that being the case, the total voltage can be written as the total current times the total or equivalent resistance. And that happens to be equal to V1 plus V2 plus V3, right? The sum of those things. But I can write each one of those voltages as I times R1 plus I times R2 plus I times R3, just using Ohm's law all the way through. And since the current is exactly the same or equal, it cancels out of every term. And that means that we can find the equivalent resistance of resistors in series by simply doing what? Just adding them up, right? So between Ohm's law, these two rules, and our derived result for the equivalent resistance, we now know what happens when you hook up resistors in series. I think you know maybe where this is going. Because if we do it in parallel, let me make just a little bit of room here. Just move that over right there. If we do this in parallel, what happens to the current as it comes out of the battery there and it gets to that first junction? What is a charge forced to do? Well, you can't split a charge, but it's forced to make a decision, isn't it? The charge has to go one way or the other. The charge behind it has to go one way or the other, not necessarily the same, right? And so at that junction, we have a split in current. What has to be true, though? Think about it in terms of water. If you have 10 gallons flowing into a split in a hose, and one of those hoses has 8 gallons flowing down it, where'd the other 2 go? To the other hose, didn't they? Right? You can't make or destroy charge, right? If you have a certain number of amps going down that wire and it splits, okay, if 10 amps is going down the wire and 6 of them go through one side, where did the other 4 go? Other side. So in other words, current is shared, right? It's split up. The sum is true, right? So the total current coming out of the battery is the sum of currents that are going through all the individual branches in the circuit. It's shared. The thing, therefore, that must be the same is what? The voltage. Voltage out of the battery is equal to the voltage across all of these elements. I should have put V's on those. And you can, I don't know if you can kind of see it almost in the drawing. This side of the battery, the positive side, is connected to this side, and that side. Those are all positive sides. And then this side of the battery is connected to all these negative sides. So whatever the drop or increase across this battery is, it has to be the same drop across all 3 of these because of the fact that all 3 ends of these resistors are all individually connected to that battery. The potential difference across them is exactly the same. So if that's true, right? And I take my current equation here. I actually don't want to draw it that way. So my current is equal to I1 plus I2 plus I3 plus ... Current, according to Ohm's law, is V over R. So that's V total over R equivalent or total. And that's equal to V1 over R1 plus V2 over R2 plus V3 over R3. But what do we know about all the voltages? They're all the same. So they all cancel out. And I get 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ... So, in parallel, current is shared, voltage is the same, and we have the inverse of the resistances adding together to give us the inverse of the equivalent resistance. I want you to know that I have made no factual errors on the screen as far as I am aware, but there is something very wrong with what's on the screen. No, you're not seeing it? Flip back in your notes to the series and parallel rules for capacitors. I'll save you some time. When capacitors are connected in series, how do you find their equivalent capacitance? 1 over C equivalent is equal to 1 over C1 plus 1 over C2. And when capacitors are in parallel, what do? You add them together. It's exactly reversed. And for somebody like me, who has trouble telling the light right from left, and up from down and all that kind of stuff, you want to know how many times I make this mistake? Always. Right? So you got to call me out on it. If I manage to get the wrong rule, I say, hey, resistors in series, add their inverses. I did it wrong. Okay? I usually have to have like this cheat sheet. I have to have the capacitor cheat sheet and the resistor cheat sheet out while I'm doing this stuff because I, for the life of me, can't remember which is which. So, series and parallel connections, those are consistent. I can get those every time, right? But which equation to apply to that situation, it's all a jumble in my brain and it doesn't come out correctly at all. So just watch out for that. And I call it out. Some of you are like, oh, great, Mr. Balogh, now you told me I'm not going to be able to do it either. It's important, right, that you realize that they are reversed from each other, right? You don't treat a capacitor the same way you treat a resistor mathematically. Series resistors just get added. So what happens to the total resistance when you put resistors together in series? Does it go up or down? It goes up. If you want more resistance, you connect things in series. But usually we're going for less resistance. We usually want electronics to be as efficient as possible, to have the least amount of resistance that's not going into heat or work or something like that. So how would we hook up resistors to be the least resistant? You do them in parallel. Okay? So that's where some of those direct applications come from. All right. Back to, the videos. I'm going to really find a better way to flip back and forth between videos and my iPad.
These two.
We did that.
The resistance of an electric resistor is proportional to its length, inversely proportional to its area, and proportional to its resistivity, or its tendency to inhibit the flow of electrons. This tendency to resist is something all materials have, but to varying degrees. Adding resistors to a circuit, one after another, has the same effect as making one resistor longer. These are called resistors in series. Putting resistors side by side increases the area through which the current can flow. These are called resistors in parallel, and they have a lower resistance than either one alone.
So kind of just another way to visualize or conceptualize what's going on with series and parallel. What did the series do? Made them longer, right? And because resistance scales with length directly, but then resistors in parallel makes what bigger? The cross-sectional area. And that's in the denominator, right? So it scales inversely. All right, let's do a quiz.